group here for this in very interesting meeting. He did 100% of the work.
100%.
Right. We just were noise fluctuating.
Because these are the bias.
Right. All right. I'm not going to talk about cracks. I'm going to talk about nucleation of cracks, of the growth of it. The idea is you have material that is nominally pristine. For optical purposes, it's transparent, not scattering light. And there are probably defects on a smaller scale that influence the behavior. But I'm interested in this nominally homogeneous material in which, under some conditions, a cavity or a crack pops up. I want to see what the criteria could be for such a nucleation event. This work was done with Long Guo, sitting somewhere over there. He does all the experiments. I get to talk about this, right? Problem has a rich history. It goes back to Gent and Lindley from 1959. They were interested in the same problem, and they used what is now commonly known as the poker chip specimen, a cylindrical specimen with a thickness that can be varied. It is actually a derivative of a specimen that the ASTM designed for adhesive strength measurements way back in 1935 or something like that. The idea is you take your specimen, which is this gray box, diagram courtesy of Oscar Lopez Parmes. You attach it to two rigid cylindrical substrates on either side and plugs, and pull at it in uniaxial tension along this. The specimen elongates, but the diameter contracts in the midplane, and you form a waist of this kind. Jet found that if you vary the thickness of this layer, you get different responses macroscopically in the force elongation behavior. And as the thickness decreases, thickness of the specimen decreases, you get a stiffer response, and at some critical point, there's an event that happens. And he describes it in his paper as an audible pop. And associated with that, there's some internal damage, which he visualized after the test was done by sectioning along the bit plane and finding that depending on the thickness, you get different types of crack patterns on the cross section. Very thick specimen, you get a vertical line like this, perpendicular to the midplane. And very thin specimens, you get a distribution of defects that are all over the midplane of the specimen. He also measured the load at which this happens and found that in different materials, they exhibit a similar behavior, that as the thickness increases, the critical stress necessary to pop the flaw decreases and reaches an eventual plateau. There's an immediate result that comes from here. If you want a high strength for your adhesive, make the adhesive thickness very small. Right? Don't need any analysis to prove that. The experiments tell you automatically. He then went to explain this thing by using the then new analysis of Green and Zerna of a spherical cavity in an unbounded medium under hydrostatic tension. At a critical value of hydrostatic tension, there's an instability that occurs if the material were neo-Hookean. The relationship between the pressure applied, hydrostatic pressure applied, and the stretch at the inner wall of the cavity was given by this expression. And if you plot this, you see that as the pressure increases, the inner radius increases rapidly. When the pressure reaches 5/2 of the shear modulus, the radius runs away. Cavity instability. Ball did a bifurcation analysis to show this is true. But real materials are not neo-Hookean. They stiffen up as you increase the stretch, and this must clearly have an influence on the cavity expansion. If you take the same calculation of Green and Zerna and use a stiffening material, you see that the neo-Hookean runs away at 5/2 mu, but the stiffening materials are able to sustain a higher pressure without blowing the cavity. So it's not clear that what we're seeing is a neo-Hookean instability because materials are strain stiffening. There's more to the story that I won't go through, but the key point is this. If you take a poker chip specimen and stretch it, the highest hydrostatic stresses appear at the midplane, along the axis, at the point where it's attached to the end plates. We wanted to redo this experiment to see actually what's going on, not rely on post-mortem examinations of where the cracks and cavities appear. So we went to a material that is transparent, PDMS, and went to a composition 30:1 that's reasonably soft, but still exhibits a stiffening response at a critical stretch level. The main innovation we made was to make the entire system transparent so you can watch what goes on and not infer what goes on from postmortem. So we have a PDMS specimen, cylindrical, 25 millimeters diameter, thickness variable. On one end is a very well polished PMMA cylinder that is completely transparent. On the other side, there's a polycarbonate cylinder, which is tougher and can be used to drill holes and things like that. And you can see the assembled picture out here. So the polycarbonate piece has a thread in it to attach to a loading device on the top. The PMMA is perfectly transparent, so you can look through from below into a projection of the entire cylindrical volume of the specimen. We make PDMS the usual way. The two sides of the specimen are decorated with speckle patterns to be able to measure local deformation or the extension in the line of the axis. The specimen is sitting somewhere here. It's attached to an instron frame on the top so we can measure the load. This measures the side displacement so you can measure the strain, nominal strain. And from below, we have a video microscope that's able to look through the entire thickness of the specimen and time resolve it by videotaping at a frame rate of about 15 frames per second. Want to navigate you through what you're going to see in the experiment. We're looking through the bottom of the specimen. The PMMA cylinder is held in place through 4 pins. These pins are going to occlude the field of view a little bit. So you can see cylindrical specimen is sitting here. These are the 4 pins that are holding the PMMA cylinder and occluding the view. But in the central portion of the cylinder, where we expect things to happen, you have a clear view of the entire true thickness of the adhesive or PDMS layer. All right, now I'm going to show you 4 videos of experiments that were done on specimens with different thickness. So once again, for orientation, that's the entire cylindrical diameter of the specimen. And as we load it up, it's going to be pulled out of plane. The mid plane is going to come through a wasting, and you'll see the waste formation. And then we'll see what happens further. Right? Video play. Okay. No. So there's the mid-plane wasting. Load is increasing. Load. And there's a critical point. Load starts to drop, but you can see associated with that, there's something going on over here and something from this side. And they approach each other and sever the specimen into 2 pieces. And we know from the geometry of this that it's nucleating at the outer surface for a thickness of 5.3 millimeters in diameter, 25 millimeters. The nucleation of the cracking event in this case was at the outer surface, meaning it's influenced by surface force. This is not what we're interested in. We want to do interior nucleation. So decrease the specimen thickness. Once
What's
again,
the radius?
25 millimeters. And the thickness is now 2.8 millimeters. Hope it's too plain. Yeah. And if you were observing through that, we saw something nucleate here. This is completely in the interior of the specimen, where there was no visible, optically visible prior flow, and it continues to grow, approaching the symmetry of the object with a crack in the middle of the diameter of the specimen. One crack, interior nucleation. So, but I don't know whether it's nucleated entirely in the interior or what one of the interfaces is a delamination, right? I neglected to mention that we prepared the specimen surfaces in such a way that there was good bonding between the end grips and the PDMS. In any test, delamination occurred with discarded reference. So all the results I'm reporting are those in which the cracking nucleated in the interior of the specimen thickness. How do we know that this was an interior of the specimen? Two ways. First, after it's broken, you can go and see whether there was residual PDMS on either side of the broken piece. And yes, there is. And then I'll show you some X-ray images where we did real-time observations to indicate that the nucleation occurred in the interior. So the nucleation, if you notice, didn't occur at the center. It occurred biased at some distance from the center. And that's going to be important. Then there was one nucleation which continued to swamp through the entire specimen. Now let's change the specimen thickness a little bit more. Now, once again, you see loading, but the diameter contraction is a little bit smaller, depends on the thickness of the specimen. And then first nucleation occurred somewhere here, it grows. But it's unable to grow beyond a certain position. Associated with the nucleation, there's a load drop. So that first nucleation was similar to the previous thickness. Now, the second nucleation occurred at some distance from the first one. Associated with that, there's a load drop. And it grows for a little distance and then it stops. When the second one nucleated, you may have observed that the first one shrunk a little bit from the elastic unloading of the neighborhood. And a third one nucleates a little bit at a similar distance from the first two. And eventually the specimen ruptures into two pieces. So we can play this game, right? Go to smaller thickness still, and you expect something similar to happen. And I'm not showing you all of the time steps. In some places, I'm dilating time so you can see the features. In other places, I'm squeezing time so you can see the features again. But time is not an important parameter in this problem. I'll just let the video speak for itself.
Sure.
So if you observe carefully, first nucleation occurred there. It triggered a second one. That one stopped, triggered a second one. Then there was a burst. And then that triggered other nucleations. The cracks all stop at some small extension and then nucleate new ones. And it's completely dominated by nucleation. They don't grow, they're unable to extract energy from the neighborhood. And they continue to nucleate until the entire surface or the cross-section is filled with nucleated cracks. The deformation then continues to increase the rupture at some later stage, way beyond where I've shown you the videos. All right. So that's what goes on as a function of the thickness. The thickness is the only length scale in this macroscopic problem, right? As the thickness changes, the confinement changes, so the ratio of the hydrostatic tension to the shear energy changes, and therefore you see different response behavior. Surface nucleation when the thickness is very large, one crack dominating when the thickness is a little bit smaller, 3 cracks, 100 cracks, 200 cracks, depending on the thickness. In a very thin adhesive layer, you would see very nice nucleation over the entire cross section before. So if you look at the specimen at this point, it looks like a honeycomb. It's got all these multiple cracks. The gap between the cracks is filled with highly elongated materials that then sever by other mechanisms much later. All right. So that's the experimental observation. Now we need to figure out, there are some kinematic quantities that we can extract from this, but we also need to figure out what criteria for nucleation of cavities can we develop from. This shows the nominal stress versus the normalized displacement of the entire gauge section as a function of the thickness. Thin specimens on the left side and thicker specimens as you go further. The thicker specimens exhibit a significantly nonlinear response. The underlying PDMS is a function of strain. The thinner specimens are so heavily constrained, they don't strain very much before the cavities pop. So they are almost linear up until the fracture initiation, nucleation. The solid lines are the experiments. The dotted lines are a calculation using simple elastic response of a model of the 13:1 PDMS using the Oscar-Lopez on a strain energy function. The simulations were terminated at the load point at which the experiment indicated that there was nucleation. So simulations are not predictive. They're just identifying what the stress state in the specimen is at the time of onset of the fracture. If you plot the normalized load to failure, normalized by the cross-sectional area, and normalized by the modulus, as a function of the thickness of the specimen, you see the big circular points are the experimental data, and the cavitation criterion of Gent, if you used it, would predict that nucleation of these cavities must have occurred when you reach this stress level. We've gone 2 to 5 times that level and still not cavitated, so clearly it's not, the cavitation criterion of 5.5 mu is not predictive for materials that strain stiff. There are the diamond points that indicate surface nucleation. One might think that the Gent criterion seems to match this very well, but the mechanism of nucleation is completely different. So any coincidence here is fortuitous. These are cracks that are nucleated on the surface. The prediction is for interior nucleation. So a little bit more of the diagnostics of what's going on. How do we know where the first nucleation occurred? So we redesigned our apparatus to be made of a material that is transparent, nearly transparent to X-rays. And PDMS cylinder is here attached to the end parts, and you apply load manually on this by turning a screw. And so you can preserve the load and do an X-ray image on that. So you in long would use a wrench to incrementally load the specimen, observing it inside an optical microscope. Stop the loading when we observe the first nucleation of the crack. Preserve the displacement constraints so the crack remains open, and put it in the bay of an X-ray tomography system and visualize where the crack is. So this is one such image. That's the diameter of the specimen, and you see there's a crack in some place over there. This is a cross-section across the thickness, and you see the nucleated crack. It's a small slanted crack, about 1 millimeter in size already. It opens up into an ellipsoidal shape. It's inclined at an angle to the axis of the cylinder, but most importantly, it's removed from the interface between the PDMS and the PMMA. It's completely in the interior by a few microns at least. So this is how we know that it is clearly interior nucleation and not interfacial fracture. If it's interfacial fracture, that's a different problem. Others are interested in it, and we could talk about that, but these are clearly interior nucleation. The same specimen, if you load it up a little bit further, may nucleate a second crack. First crack is from the previous slide has grown up to here. The second crack nucleates. It also has a similar geometry. It's not crack of some kind removed from the interface. And we get carried away with a lot of these images. You can basically track the nucleation. This is for a specimen that has a very thin adhesive layer. The orientation seems to depend on the layer thickness. It's progressively more aligned with the axis of the cylinder as you make the thickness smaller. All right. When the crack grows at an angle first, reaches the interface, but doesn't penetrate the interface. But I don't know if you can see it in the screen, but it's a crack that's parallel to the interface, but distinctly separated from the interface. So it moves along at an angle, comes parallel to the interface and continues along as a very highly mixed mode crack with the attendant twisting, cracks, fragmentation, and things like that. All right, what more can we get from the experiments? The most surprising thing was that the nucleation was not at the center of the specimen. If you do a stress analysis of this specimen, the hydrostatic tension is the largest along the axis of the specimen, and one expects that nucleation driven by hydrostatic stress would be at that location. But consistently over many, many specimens with a large scatter, the nucleation was clearly away from the center, but with an average location of about 0.45 of the radius of the specimen. There was some speculation that this might have been due to bending asymmetries introduced by the loading device. So we decided to put a sleeve, a cylindrical sleeve around the specimen, sliding fit, so that it would allow uniaxial motion, but not allow bending. And those specimens also exhibited nucleation at points indicated by the asterisk, so away from the center. We'll file that away. The distance from the rigid surface where the first nucleation occurred. This needs a little bit interpretation. When we see the nucleated crack, it's already about 1 millimeter length. We don't know where it nucleated, whether it was at the centroid or whether it nucleated at one end and propagated towards the other end. Anyway, centroid is an easily measurable quantity. So you look at that, and within a large scatter band, it seems to be about 20% of the thickness removed from the interface. That's where the nucleation occurs. These are simple kinematic measurements of the experiment. We need analysis later on to back it up. The last kinematic quantity that we can generate from this is for the multiple nucleation. What's the distance between the nucleation sites? So you identify the center of each one of those nucleated cracks, find the distance between them using tessellation, and then plot that as a function of the specimen aspect ratio of diameter to thickness. And the large lines show you the distance, the standard deviation of the distance between nucleation sites, but within that distribution, you see that the distance between nuclei is about 3 times the thickness of the specimen. Once again, thickness of the specimen is the only dimensional quantity that exists in here. So it has to scale with that. Why 2.78? Again, it needs analysis to firm that up. How much time do I have? I'm out of time, right? You anticipate nucleation to occur at this location, but the actual location is somewhere here. Seems that what we need is a condition that is competitive. You need pressure that is high enough, that means closer to the center. You also need some strain energy in order to pop cracks. This is an incompressible material. High hydrostatic stresses don't provide any energy associated with it. So you need shear deformations, meaning you have to go away from the center towards the free surface where the shear energy picks up. So you need to be close enough to the center to have high hydrostatic stress, far enough away from the center to have larger deformation energy. Somewhere there's a sweet spot. So we did a series of calculations of the stress state in the specimen. Since I don't have enough time, I will just say we did a stress analysis of this and found that if you reach a critical state as a combination of hydrostatic stress and shear energy, you find a criterion for nucleation. I'll refer you to later discussions for details of that. Well, with that, let me stop and throw it open for questions. Thank you.
Questions? Beautiful. Suppose you imagine going to thinner and thinner and thinner samples with no limit. What do you imagine happens as you go to really thin samples?
Well, you break it up into filaments probably. Each nucleation is going to grow smaller and smaller amounts, and eventually it's going to nucleate everywhere, but with smaller size scale. In the end, it's going to just fibrillate the entire polymer.
Can I comment on that?
Sure.
If you don't think in terms of, physical scales, molecules, right? With still in a continuum world, let's say in a continuum world, right? The role of compressibility will increase dramatically in thinner and thinner specimens.
Right, but there's no energy associated with that pressure buildup.
It will be, shear will come naturally, because here you presume it is incompressible from the very beginning.
Right. So at some scale, which has to go to the scale of the molecular structure, incompressibility will break down.
No,
Because they're not
forget about your plate is 1 mile in diameter.
So if there are flaws that are on the range of 100 microns or so, we should be able to see it. These flaws that exist in there are sub 100 nanometers and optically not visible. So any fluctuations that appear below that scale are the ones that are going to influence nucleation as you go towards thinner specimens.
Ravi, if your specimen were 1 mile in diameter and 1 meter thick,
you wouldn't be able to pull it.
say again? He's an experimentalist.
Yeah, but I had very beautiful work, really interesting and new. And I'm just wondering, I mean, you're always spoke in terms of alpha, the aspect ratio, but it seems to me that the size also has something to do. If you take the same aspect ratio and you make it 10 times smaller, at least from our experiment, there is a difference, because energy is
Might be a different.
Once he stops share screen, you can share screen.
yeah, I don't want to do a mile-long experiment. Yeah, but you went up. I want to go down.
No, but I think when you go to that smaller size, you again getting to dimensions that are of the order of molecular intrinsic product distribution.
I was just thinking instead of millimeter, you go down to 100, a factor of 10, because they are still, it seems to me that the energy being an intensive quantity, if you make things smaller, the balance between the two might change.
Thank you.
Thank you.